Everyone, how's it going? Today we're going to talk about the much awaited topic in physics. Yes, we're talking about Newton's laws of motion. This is one of the biggest milestones in classical physics, and it's super, super cool because once you learn these laws, you can solve almost any physics problem in classical physics. And I'm not kidding. So before we dive into Newton's laws of motion, I want to talk about where these laws apply, because if we try applying them in other situations, they will not work. All right. So to do that, I need to explain what an inertial reference frame is. If you remember before, I talked about what reference frames were. Reference frames were just a sort of like your space, right, that you're in, plus a clock, right? So your nice little clock here. So that clock, so space-time. So you have space, which is maybe defined in terms of 3 dimensions. You can choose x, y, and z to be those coordinates, and some time t. You have some clock ticking, and that is really an inertial, a reference frame. So that is what you call a reference frame. So what is this inertial? So what makes a reference frame inertial, right? Well, an inertial reference frame is a frame where things make sense. Let me try to explain that to you in a way that makes sense. So let's say you wake up in a white room, you don't know where you are, and all you see in front of you is a pendulum. Let me try to draw that room for you. So this is the room that you're in. You don't know why you're here, and the only thing you see is this pendulum bob, all right? And it's vertically down, parallel to the walls, and that makes sense, because you expect gravity is pulling the bob down, and that's why it's exactly oriented that way. Now let's imagine that you again wake up in a room, in a white room, maybe the same one, and you see the pendulum, but this time it's tilted. And it's just tilted like that. It looks as if someone's just holding it, but no one's holding it. It's just tilted at some angle. And that's very confusing. Things don't make sense. Why is it tilted? I mean, gravity is acting downwards. Gravity is acting downwards, so it should look like this one, right? It should look like this. So you're like, what? Why is that happening? Why is the pendulum tilted? All right. So where do things make sense? They make sense here. This is called an inertial reference frame. Or some people say inertial frame of reference. I don't know. So I just say inertial reference frame. This one, can you guess what this frame is called, where things don't make sense? That's a non-inertial reference frame. Something that it just doesn't make sense. What do I mean by things not making sense? I mean the sum of forces don't add up, right? You cannot explain the motion or the orientation of objects around you by the sum of the forces. Here you can. Here you say, oh, gravity's acting downwards. So here, you're like, yeah, I can explain the sum of forces. Gravity's acting downwards, and, the string is a bit tight, so that tension is, pulling it up. And that's why this bob is exactly straight. Here you're like, so here's sum of forces, which I'm going to make sigma. F sigma means sum. F means forces. I can explain the motion of this pendulum. Here I can't explain it. I see gravity acting downwards. I see the tension of the string is acting in this direction. And you're like, things don't balance out. So this is wrong. So I don't think this is an inertial reference frame. There's more to the story than meets the eye. That's what really a non-inertial reference frame means. And if you're confused, why is this happening? Why is this pendulum tilted? It's actually because this frame is moving. It's with some acceleration. So acceleration is not equal to 0 in this case. But in this case, in the above one, acceleration is equal to 0. You can confidently say that. Anyway, don't worry too much about these. I don't know if even textbooks talk about this, but it's important to understand that there are places where Newton's laws will not work. And that's because you're not seeing the whole story. Now, you might be questioning, Earth is actually rotating, right? So Earth has an acceleration. So how do Newton's laws apply to Earth? Well, they approximately apply to Earth. And if you are a physics major and plan to study classical physics, you will find beautiful examples where experiments conducted on Earth don't actually follow Newton's laws of motion. And you have to take into account the rotation of the Earth. If you're really curious, search up the Foucault pendulum. But I'm not going to talk about this because this is a basic physics course, and I'm not really going to get into that. So now that I talked about where Newton's laws apply, and if you didn't get any of the stuff above, just ignore it. That's okay. They only apply to inertial reference frames, though. Let's talk about Newton's laws, because that's why we're here, right? So what are Newton's laws of motion? Well, there are 3. I'll go through them one by one, and I'll try to explain them best I can. So the first one says that, let's say you're an observer in an inertial reference frame. If an object is at rest, meaning it's not moving, it'll remain at rest. And if an object is in motion with some velocity, it'll remain with that velocity, unless some external force comes up and compels it to do otherwise. Now, in plain English, that means if you see a ball that's just sitting there and you kick it, it's going to move. It's logic, right? But, you need fancy language and you need to be specific when you want a law of physics. So, essentially, Newton's first law of motion is saying that velocity is constant if the sum of forces acting on an object are 0, if the sum of forces is not 0, then velocity will change. And we'll put a little arrow on top of the v. That means v is a vector quantity. Yes, you guessed it. Now, it's interesting that they used velocity and not speed. That means that not only does the magnitude of the velocity, meaning how fast an object is moving, is at play here, it needs to be constant, but also its direction needs to be constant. That means if you have a ball that's moving, let's say, northwards, it needs to continue to move northwards. If it suddenly moves, southwards, eastwards, or in some other direction, then there is some force acting on it. That also applies to spinning objects, because the direction of a spinning object constantly changes, right? If something's moving in a circle, the direction keeps changing. So even if its velocity is its speed is the same, not velocity, even if its speed is the same, the velocity is changing because it's moving, it's moving in a circle. Its direction keeps changing, right? Anyhow, this is the first law of motion. The second law of motion is more fun. I don't even have to say it. I can just write it down. Force is equal to ma. I said it. Okay, so force is a new quantity. I haven't defined it before. Force is just defined as mass times acceleration. And force is a vector quantity, as you can see from the arrow above. I don't think I use arrow notation. Arrow means something's a vector quantity. I'm not going to put an arrow on top of mass. Mass is not a vector quantity. So the force takes the same direction as the acceleration. All right, this is something to notice here. Force is equal to mass times acceleration. Whatever A's direction is, if A is eastward, force will also be eastward. But the magnitudes will not match because you have this m here, right? Which whatever the mass is, so m is mass, in case that wasn't clear. Whatever the mass is, that affects the force. So if you have something that's more heavy or has more mass, you're going to have to apply maybe a greater force on it, or you're going to have a higher force. Okay, that's what F is equal to ma means. Sometimes they will write this law as the sum of forces equal to mass times acceleration. I like this form better, so I'm going to box this form. This means you have to take into account all the forces, add them up, and then you can say that's equal to ma. And we'll talk about all the different, maybe not all the different types of forces, but the most popular ones. And those are what you need to take into account. Now notice if you look at the first law, and I have to do this, I'm sorry. Remember in the first law we said if the sum of forces is 0, then the velocity is constant. Well, I can directly prove this from the second law. So that means if sum of forces is 0, so I can say ma equals 0. That implies that either m is equal to 0 or a is equal to 0, right? So one of these has to be 0, or both of them have to be 0 in order for ma to equal to 0. Now we know that mass is usually not 0, right? Well, when I say usually, I mean it's never 0 for something that's moving, because objects always have mass. So this scenario doesn't make sense. Acceleration has to be 0. Remember what acceleration was? Acceleration was equal to the change in velocity or the change in time, right? Now, if acceleration is equal to 0, that means this delta v over delta t is equal to 0. That means if I move delta t to the other side, that means delta v is equal to 0. Delta means the change in. If the change in something is 0, that means it's not changing. If it's not changing, that means it's constant. So that means v is constant. And we just proved Newton's first law from Newton's second law, actually. Or we kind of verified Newton's first law by plugging in this delta, or not delta, by plugging in sigma f is equal to 0. The sum of forces is equal to 0. I should probably put a little arrow up here. But yeah, sigma f is equal to 0. We plugged it in here and we proved that velocity is constant. So this is verified by Newton's second law. Okay, so that's Newton's second law of motion. It's a wonderful equation that we're going to use a lot. All right, we're finally down to the third law. This is the law that you've all been waiting for. It's the third law of motion. The third law of motion says that for every action force, there is an equal but opposite reaction force. The best way to understand this is just to look at a simple example. So there's like a block on the ground. There's gravity that's pushing the ground or pulling the ground downward. At the same time, there's a force that's pushing the block upward. And that's the action-reaction principle. And these two forces have to be exactly the same in magnitude, but opposite in direction. So let's call this upward force as N, and let's put arrows on all of these. I'm going to call this gravitational force as uppercase G. So G, the gravitational force, has to equal to N, but in the opposite direction. So that's why we have a negative sign over there. So let's say if G is 10, then N will be negative 10. Or if G is negative 7, then N has to be 7. So they're always opposite pairs, action-reaction pairs. Okay? So these are equal but opposite forces. And that's what Newton's third law says. Now, you might think, okay, this is great. I don't really know how I'm going to use this. Newton's third law is going to help you solve all your force problems. I'm telling you. This is, by the way, called a force diagram. And any physics problem that you come across, you're going to be drawing these because these are going to solve all your problems. I'm telling you, force diagrams are really the way to go. And once you've mastered them, any physics problem is solvable. It becomes so simple. Well, not any physics problem, any force-related physics problem becomes solvable. Now, before we move on, before we go ahead and start talking about force diagrams and how to use them and the different types of forces, I want to address a misconception some of you might have. I know I had it when I first heard about this action-reaction principle. What I thought was, and some of you might be thinking the same, if there's always an action-reaction force pair that are equal but opposite, doesn't that mean that they cancel out and there are no forces then, and that means nothing moves and everything should always be stationary? For me, I was like, Newton's third law has to be wrong. This doesn't make sense. How is this being taught in textbooks? Well, the idea is the forces only cancel out when they're acting on the same object. When forces act on two different objects, they don't cancel out. So that's really the idea we need to look at. Let's try to understand this better. If two balls are headed towards each other and they collide, they then move in opposite directions. And that's because the moment they collide, ball 1 applies a force on ball 2, and ball 2 is applying a force on ball 1. And this force compels it to move in this direction. This one compels it to move in the opposite direction. So that's what it means. The forces are acting on different objects. If you had a single ball and someone was pushing it this way and someone else was pushing it this way, then the forces would cancel out and it would remain stationary. This is the best way to try understand, I think, the action-reaction force pair and why things move despite these being equal but opposite. It's acting on different objects, that's why. Okay? So now let's try to understand force diagrams, and these will really solve all your problems. I'm not kidding. The best way to understand these is through an example. So let's dive right in. Let's say there's a pendulum. And if you don't know what a pendulum is, it's just a fancy word for having a string and a bob attached to it, like a little ball or something, and having it hang from some sort of support, like a ceiling. Okay, so this is like a ceiling. That's a simple pendulum. Now, let's draw the forces on this pendulum. Whenever you're doing a physics problem, you have to think about where this problem is happening. Usually it's happening on Earth, unless the problem specifies otherwise. So whenever something's acting on Earth, think about the apple that fell on Newton's head. There's going to be gravity. So you have to draw the gravitational force, and it's going to act downwards. I'm going to call the gravitational force as capital G. Now, if the gravitational force is acting downwards, and it's the only force acting on the bob, that means the bob has to move downwards too, remember? Because the bob can only be stationary, according to Newton's first law of motion, if the sum of forces acting on it is 0. And is also according to Newton's second law. Force needs to be 0. The sum of forces needs to be 0. So there has to be another equal but opposite force. And this is also according to Newton's third law, the equal but opposite force. What is the equal but opposite force? The equal but opposite force has to be the same magnitude as gravity but in the opposite direction. So it's going to go upward, and let's call it T. This force is actually called tension because it's acting on a string. Whenever you have a force acting on some sort of a string or on a spring, it's called tension. It's a kind of force that's pulling on something. It's making something tight and taut, okay? Now, we know that from the third law, T is equal to minus G. The tension is the opposite of gravity. So this is the first force diagram that we have. I'm going to talk a little bit about gravity. The gravitational force is actually given by a nice formula called mg. And this looks very familiar to, remember, Newton's second law, ma, except g is now taking the place of a, and this g is called the acceleration due to gravity. I think I talked about this before, but let's just recap on that. And it's equal to 9.8 meters per second square, and usually they put a negative sign to say that gravity is acting downwards, all right? So G is equal to mg. The gravitational force is equal to the mass times the acceleration due to gravity. And just to do a simple example, if let's say something weighs 10 kilograms and the acceleration due to gravity is 9.8 meters per second square, then its gravitational force will be the mass, which is 10, times 9.8. And this is 98. And where are the units? Well, that's kilograms meters per second square. Or if you don't want to write kilogram meters per second square, you can just write N, which stands for Newton. Yes, Newton was the one who came up with all these laws, so we call one kilogram meters per second square as a Newton. Okay? It's a lot simpler. All right, 98. Now, this is for Earth, though. This G only applies for Earth. If you're on the moon, the value is going to be different. And that means your gravitational force is going to be different. All right, so let's just go through a simple example. I don't know what the value is on moon, so I'll make a made-up planet. So on my made-up planet, the mass is still 10 kilograms. This isn't going to change. But now the acceleration due to gravity, let's say, is 3 meters per second square. So in this case, the gravitational force G is still equal to mg. That doesn't change, but it's 10 times 3 now, which is 30 newtons. So see the difference, 30 versus 98. That means on this other fictitious planet, the object's going to weigh less if it goes on a weighing scale. It's going to be lighter on that planet. So if you go, let's say, to moon where this G value is lower than the one on Earth, you're going to feel lighter if you walk around. You're going to feel like you're flying, or that you can like jump around. Your body's going to feel a lot less heavy. It's interesting, right? And if any of you have watched the WALL-E movie, that's why the humans that grew up on the spacecraft, their bones are more like out there, right? Their bone density is less, and that's because the gravity that they were exposed to as they grew up was a lot less than what was on Earth. So their body was able to grow in different ways. So acceleration due to gravity plays a huge role on the gravitational force. Okay? So that's what G is. And now that you know the gravitational force, you can calculate the tension. The tension is just Whatever you got for G, but opposite. So if you got G as 98 over here, it's the T value, the tension value is just minus 98 newtons. And in this case, it's just minus 30 newtons. Hope that makes sense. Now we're not quite done yet. There is one more force, well, actually two more, which are quite interesting. So let's look at a block, a simple block on the ground, all right? Now what's acting on this block? Yes, you guessed it, gravity. Gravity is acting on the block. I will call this capital G. There has to be a force that acts opposite to gravity. Is it going to be called tension? No, there's no string, there's no spring, there's no tension. But there is a force and we must give it a name. So I will call it N. And it is called the normal force. And that's because it's always perpendicular to the surface. If the surface was inclined at an angle, so the block looks somewhat like this, gravity, so when I mean inclined, this is the ground, okay? Gravity will still act downwards, which is in this direction, but the normal force will be perpendicular to the surface. Perpendicular means 90 degrees to the surface, 90 degrees. So if I was drawing this with a ruler, I would make sure, okay, it should be 90 degrees oriented. And that's the normal force. And that is G, okay? Not lowercase g, that's acceleration due to gravity, uppercase G. All right, and now you can see that the forces are not opposite. So what's going to happen? The block is probably going to move downwards. It's not going to be stationary. Anyway, but in the above case, it is. It is downwards. And well, it is upwards, and they cancel out and it's stationary. All right, so that was just a block and gravity acting on it. Now let's say you have a block, gravity's acting on it, so you have G, and we have normal force N. But now there's another force where someone's just trying to push the block, okay? I'm just going to call it capital F. So someone's just trying to push this block. So it's pushing motion, they're pushing it to the right. Now, if you've ever tried pushing something like a cardboard box along the floor, you've always felt some resistance, right? We call that as friction, and it's always in the opposite direction. So if you're trying to push something to the right, it's going to try to move things to the left. And we call this the force of friction. And I think I'm going to just call it F with a, maybe, I'm just debating what to call it. I'll just call it Fs for now. All right, so we'll call it the force of friction. So that is F over there. Now the idea is, what is friction? How do I calculate it? Well, it's very interesting. Friction is related to normal force. So you can think about it as, normal force kind of tells you how squashed something is to the ground. So if you squash something against granite and try pushing it forward, there's more friction compared to if you just, try to push it along without really squishing it to the ground. When you squish something to the ground, you increase the normal force, by the way, because it's not only now gravity, it's also whatever force you're pushing down, right? So the friction force is directly related to the normal force, and there's this nice equation that puts them together. The friction force is actually equal to mu times the normal force. And it's a magnitude-wise, I would not put arrows in this case. It's the magnitudes. Because the friction force and the normal force are perpendicular, so their directions cannot be equal in any way. So we call this mu. What is mu? Mu is called the coefficient of friction. So coefficient of friction. And that's how the friction force is related to N. Now, I actually didn't give you the complete story. There are different types of friction. And I know at this point you're thinking, why did friction have to exist? Well, I'm sorry, but friction allows us to sit down and not slip away. So let's just be grateful, for friction, towards friction for a moment. So friction has three different types that we're going to discuss. There are actually many more. They are static friction, kinetic friction, and rolling friction. And they all use the same equation, so stop complaining. So static friction means, well, the best way to explain this is just imagine, again, the block. I'm not going to draw gravitational or normal force to keep things simple. Let's say a little person's here and they're really trying to push this block, but it's just too heavy. It's just too heavy. Then the only force that we can consider is the force that this person is using to push the block, F, and the friction force, which we'll call Fs. And this Fs is actually the static friction force. all right? Because the object is not moving. The person's trying their best to push the block, it's not moving, and the block is stationary. But they're still applying a force. And we want to know how much is the static friction force. The static friction force, Fs, is equal to mu s times n. And this is called the static friction coefficient, or the coefficient of static friction. And this is something that scientists have calculated. It's not something that you will know off the top of your head, okay? Now, let's say the person, I don't know, works out a bit and becomes a bit stronger and is able to finally get this block moving. So the force that they're using is actually pushing the block. The block is starting to move finally. Now, we have to use a different friction force. We can't use static friction anymore. We use something called kinetic friction, which I'll call Fk. And Fk uses the same formula as the static friction, but instead of having mu s, it uses mu k n. So that's called the coefficient of kinetic friction. By the way, if you're confused about the symbol mu that I drew, mu is just a Greek symbol, mu, okay? It's just like a U that has a long side attached to it. So that's mu. So that's Fk. And then there's something called rolling friction, which I don't know how often it's even discussed, but you have a ball and it's rolling. Instead of being slid, it's now like actually like rolling on the surface. And Fr is equal to mu r, and yeah, you guessed it. It's all the same. You have coefficient of rolling friction. These are values that are given to you. You do not need to know them off the top of your head, okay? These coefficient values. Now, how do they help you? You can figure out the acceleration using these values. So you would use Newton's second law, sum of forces is equal to ma. And this would help you decide what to do. If the object isn't moving, you would say, okay, the force that I'm applying minus, because it's in the opposite direction, the force of friction. And in this case, let's say if the object's not moving, it's static friction. And since it's not moving, it's 0. Something like that. If it is moving, then you have F minus Fk is equal to ma. Because it's not 0 now, but it's actually moving. There might be some acceleration involved. And if it's rolling, then you might do F minus Fr is equal to ma. And then you would substitute Fk, Fr with the mu n values, and you can solve for how much the acceleration is, or whatever you're trying to do in the problem. Now, I'm not going to delve too deep into friction just yet. I think the best way to understand the friction, normal force, tension, all of these, and the force of gravity is by doing problems. So these forces, it's best to get experience, and try to experiment in nature. Try to throw things around and see how they behave, and did it behave the way you expected.